Today, I'm going to give a lecture on organic chemistry. You have the slides, so you can follow along with the slides, and I'm not sure if this is going to be one video or two. We don't do a lot with organic chemistry in this class because obviously we just don't have the time, and you need a lot more background chemistry to go into detail. But it's interesting because a lot of the molecules that you deal with in everyday life are actually organic molecules. So let's talk about what organic chemistry is. And remember, you can always pause the video. You can go along with the slides as you're going. And there's a homework assignment. I believe it's homework 11 covers this material. All right. So think about this. Outside of chemistry, if you hear, oh, it's organic, what does that mean? All right, and what that typically means to people, it's organic means, oh, it's from nature, it developed from the ground. When people say, I want my relationship to develop organically, it means I just randomly met somebody. Or organic food means technically, well, when it first came out, it didn't mean anything. It was a brand name, but people made assumptions, and so the FDA came in and said, if you're going to say organic, they set up standards for what organic means. So in foods, organic means below a certain amount of pesticides and fertilizers and things like that. There are criteria. They can't make it zero, and that's because if you're a farmer and you're a farmer on the next piece of land and you're growing things organically, but the farmer on the next piece of land is not, and they're using fertilizers and they're using pesticides, well, they deliver that from an airplane, and so you can't keep it 100% off of your field. But typically organic in that context means from nature, things like that. However, in chemistry, it has a very different meaning. All right. In chemistry, it just means it's a carbon-based molecule. So all the molecules are carbon-based, meaning a lot of carbon-carbon bonds, carbon-hydrogen bonds. All the bonds are covalent. Many organic molecules are biologically active because the biochemical molecules are also organic, and if that means they're biologically active, they'll react with things. Just as an example, DDT is this is an organic molecule. All the carbon, I'll tell you what these mean in a little bit. But this is a very, very dangerous pesticide. In fact, it's outlawed. They can't use it anymore. Very effective, but very dangerous. So organic in different, just like we've talked about this a lot in the class, the same words in different contexts can have very, very different meanings. So if someone says, oh, it's an organic molecule, like glyphosate from Roundup is an organic molecule as well. So be very careful about it. But organic chemistry means it's carbon, carbon, a lot of carbon, right? Organic molecules, mostly carbon, hydrogen, oxygen, and then nitrogen, phosphorus, and sulfur. Mostly carbon, hydrogen, and oxygen. Nitrogen, a little bit less. Phosphorus and sulfur, not quite as often. They're all nonmetals. So are they ionic? No. Covalent? Yes. Can they be polar? Okay, remember what it takes for a bond to be polar? Polar means there's a difference in attraction for electrons. Remember, oxygen and nitrogen have very strong attractions for electrons, so absolutely organic molecules can be polar. And the shape stuff we talked about before can be very important as well. All right. So typically there's two parts to an organic molecule. There's the carbon part, which is called the carbon skeleton, and then there are what are called functional groups. Functional groups are literally just what they sound like. That's where the reactions take place. That's where the molecule gets its function. So most of the chemistry is about the functional groups. And all I want you guys to be able to do in this class is recognize organic functional groups. We're not going to do organic nomenclature because we just don't have time. We're not going to do a lot of the chemistry of organic molecules because we just, that's not what this class is about. But it's interesting, and I may have mentioned this. I changed my major to chemistry when I took organic chemistry. I found it fascinating because my interests are biological, and organic molecules, many of them are biologically active, and it's the first step to understanding biochemistry. So people who take biochem need to take organic chem first to understand how those molecules work. But for this class, we're just going to recognize organic molecules. All right, so some notations. So we've done Lewis dot structures before. So for example, this is called propane. And if we did Lewis dot structure of this, we know how to do this, and we know shape-wise, right? So this carbon has 4 attached atoms, so this is tetrahedral, this is tetrahedral, and this is tetrahedral. So this is kind of a three tetrahedra on top of each other. This is what an abbreviated formula. So this molecule drawn this way is typically written this way. So instead of writing C3H8, we write C3, CH3, CH2, CH3. And if you look up here, CH3, CH2, CH3. So that means the H's are attached to that carbon. The H's are attached to that carbon. And then a lot of times we just do what are called line angle formulas, which is this. I call it squiggle notation. But what this is every corner, every vertex, or every end is a carbon. So this is a carbon, this is a carbon, and this is a carbon. And then there's enough hydrogens to fill the valence. If it's not a hydrogen, if there's an oxygen, the oxygen would be drawn. So remember, valences, carbon likes to have 4 bonds. So this is 1 bond. That means there'd be 1, 2, 3 hydrogens. This carbon has 2 bonds. So that's 1, 2 hydrogens. It's the same as this. This carbon has 1 bond. So that means 1, 2, 3. So this is carbon, 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 3 hydrogens, 3 hydrogens, 2 hydrogens. So just being able to recognize that. So if we back up to here, so right here, this is a carbon, and this has no hydrogens because it's got 1, 2, 3 chlorines. This carbon has 1 carbon, 1 carbon, 1 carbon, so there would be a hydrogen here. These are double bonds, so this carbon here has 1 bond, 2 bonds, so there would be a hydrogen here. Right? All right, so these are just more examples. This is a Lewis structure, this is the line angle structure, and this is the condensed formula. So this would be squiggle, 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 squiggle. It looks like this, right? CH3, CH2, 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 CH3, right? CH3, CH2, CH2, CH3. Okay, this here, right? CH3, CH, CH2. And then the squiggle would just be, and we draw them bent like this because this is where these are tetrahedral centers. So this is kind of flipped from the structure, but you get the idea. And then this one would be CH3, CH2, CH2, C double bond oxygen, and then CH3. So you can see the CH3, CH3, CH here, or C here. Actually, this is wrong. And then there's a CH2 here. This actually is kind of, anyway, but you get the idea, right? So this means this. All right, so we're going to talk about the basic organic functional groups. Naming-wise, again, we're not doing it, but they typically rhyme with what they are. So the word alkane, things that end in ane, like propane, butane, are alkanes. These are all single bonds. They're all very nonpolar because carbon-carbon bond is, of course, nonpolar. Carbon-hydrogen bond is nonpolar. In general, they're all tetrahedral centers. These are kind of boring. Pretty much all they do is burn. Okay, alkenes are interesting. Alkenes have double bonds, right? So this is an alkene, okay? And interestingly, around a double bond, we can arrange a double bond this way, or if this carbon went over here, like this way, see how the carbons go here and here? That means there's a hydrogen going this way and the hydrogen going this way. There's what are called cis double bonds, where the carbons are on the same side of the double bond. Actually, we refer to the hydrogens, so the hydrogens would be here and here. And there are trans double bonds where they go to the opposite side. So the double bond is here. Remember, a double bond, this is basically trigonoplanar, if you think there's a hydrogen here, right? So these are called cis-trans isomers. Isomers are the same structure, or the same formula, but a different arrangement. And that's what this is. This is a trans, this is cis. And we've talked, you may have heard of trans fats. So trans fats are used to make things a little bit more crunchy. Normally, fats tend to be cis, but there are some trans fats naturally occurring, but they change the texture a little bit. Trans fats have been implicated in some problems, and there's dietary cautions against trans fats because trans fats, the shape of them, they have trouble getting through small blood vessels, and also they're metabolized a little bit differently. Okay, but you may have heard of a trans fat means that a fat is a long chain of carbons, and a trans fat would have a trans double bond. All right. Another piece of notation that goes with functional groups is what's called R notation. If you see R, it literally means the rest of the molecule, and it means we don't really care what it is. It's not important in the chemistry. Right. I think what I'm going to do is I'm going to stop here because the next slide goes through the functional groups. So I'm going to stop here, then I'm going to go through the functional groups, and so we'll pick up for the second video.